bunch of conics, and we've actually analyzed quite a few different types of conics. So if we take two cones and put them tip to tip, we're going to generate our conic shapes. Our first conic shape is if it, and by the way, it's all going to be intersecting with a plane. So I want you to visualize as I cut through this piece, what is it going to look like? What is the intersection going to look like? What if I go right where the two touch? What's the intersection going to be? It's going to be a plane. We've analyzed the point to death. Reveal the point. Okay? Let's say I cut it right along the edge. What's the intersection going to be? It's going to be a straight line. We've analyzed the line of death before. Slope intercept form, blah, 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 right? Next up, what if I cut through exactly parallel to one of the sides? What's the intersection going to be?
Parabola.
You see it's going to be a parabola? Let's try to get a different color going. I'm terrible at drawing this. Like I said, I'm terrible at drawing this. Right? I cut it with my sword. I like that better. Okay. So this is a parabola. Next up, I'm going to slice it like here. See, when we get an ellipse, okay, we come straight through, we get a nice ellipse. Okay, and you can see, cut right through it. Last one is if I were to take and I were to cut straight up and down. You see what I get? I get two pieces that kind of look like a parabola. It's not a parabola, but if I go straight down, right through the edge, right through here, I'm going to get a hyperbola. I'm not sure how in depth I'm going to get with all this. We'll have to see. We're getting a little on time. Now, where would a circle fit into all this? Yeah, but it's just a special case of an ellipse, right? It's just if I literally went straight through that way. Okay? We're going to talk, you've learned about the parabola, we're going to talk about it a little bit more in depth, a little bit. And then we'll talk about the ellipse and the hyperbola. We'll see how far we can get with this. So, parabola. you want a complete sentence, just put a parabola is. There you have it. Now, what does this mean to us? So, the directrix is a line. Now, it's not a line that's a part of the graph. It's just sort of this. Let's do this. Let's draw a parabola. We have a focus. This is the director. And parabolas are actually used all over the place. I told my pre-calc class this. You have a parabola in front of your eye if you're using eyeglasses right now. It bends the light in a certain way so that it hits your optic nerve just right because your lens isn't working right. Okay? If you look at no, that's dumb. So let's do, if there's a satellite dish, okay, that arm comes out, it's right at the focus. Because there's some cool properties about this. If you have a parabola and there's a signal coming in and it hits, every signal, no matter what the angle is, as it hits, it's going to come and go exactly through the focus. That's what defines a parabola. That's what always has those arms. If you have like a mag light and you turn it on and you adjust it just right so that you get a nice straight beam, that means that the lamp in there is exactly at the focus, and no matter what, it hits and it exactly makes it go in the same direction. That's why when you turn it, the lamp moves and it's no longer at the focus and it scatters the light. So this is actually very, very useful. So the definition says, and I use blue for this one, that every point on the parabola, obviously it's not drawn all that great, it means that this distance right here is equal to this distance here. For every point on the parabola. That is the definition of a parabola. It goes for every point on the parabola. One way to write a parabola, right? I guess two ways. You get both of those by completing the square. So regardless of how you end up with these, by the way, when you complete the square on this, h ends up being negative b over 2a. In fact, maybe some of you haven't seen this before. If I take and I want to find the vertex, that's a local min, right? Or local max, depending on what we're doing. So if I want to find the slope of the line when the slope is equal to 0, I have to take the derivative and set it equal to 0. And this is where the formula comes from for the vertex. So you've all seen this before, right? I mean, you've seen this result before. Okay, so here's a calculus way of proving this. The non-calculus way is you have to complete the square. Factor up to a, you get the b over a, and go through the whole thing. It's not that hard to do. So, let's talk about the important features of a parabola. I'm going to stick with this one for now, just so that we can move forward. Let's talk about if it's facing upward or if it's facing downward. Consequently, if I was doing the other one, it would be facing to the right or to the left. What determines if a parabola is facing upward or downward? A, basically. vertex. Here. That's if it's in that top form there, the top left, I should say. So I wrote this a little bit differently. Find the y-intercept, you set x equal to 0. If I set x equal to 0 here, it's going to be 0 comma c. You see that? If I set x equal to 0 here, I'm going to get ah squared plus k, depending which form you're in. To get the x-intercept, for this one, I'm going to set this equal to 0, and I use quadratic formula. It's possible the x-intercepts that there are two, it crosses twice. It could bounce off the x-axis and cross once, or it may never cross the x-axis. Then you get complex solutions. Now, how would I find the x-intercept using this form here? What would you do?
Can you say that again?
I want to find the x-intercept using this form here instead of this one. So y equal to 0, then what? Solve for x, right? I'm looking for what x is equal to, right? Would you please set it equal to 0 and solve for x?